Hi everyone, I'm Monica,
Hi, I'm Matilda.
and this is our video about our rational method model.
After the earthquake, Christchurch has experienced more floodings than before. And for the last couple of years, the area downstream Bow Whale catchment have been affected more often because of the sublanding of the land. So the Bow Whale catchment is analyzed for a 1 in a 100-year storm event, and the model will result in an estimated peak flow, time of concentration, and the area of the catchment that contribute to the flow. The rational method is the most common used method for small watersheds and is given an estimation of the peak flow for a given event. The method is based on a formula shown in the PowerPoint that relates the peak flow, the drainage area of the catchment surface, and the rainfall intensity for the given event. In other words, it means that the peak flow is a relation between the total rainfall in the catchment and the losses from infiltration on the surface of the catchment.
So when we applied our model to the Bowen Vale catchment, our model calculated that the area of the catchment was just under 300 hectares, and for a 1 in 100 year storm event, the predicted runoff peak flow was 15.6 cubics, and the predicted overland time of concentration was 22.4 minutes. The runoff peak flow would be very high, and as we've seen in the past, the residual areas downstream of the catchment would be affected. For this size of a storm event, we would certainly expect flooding of the Heathcote River, especially in the Beckenham area. The purpose of our model is to calculate values for the peak runoff and the overland time of concentration, in our case for a 1 in 100 year storm event at the Bowen Vale catchment. And doing this required 6 inputs. We needed a digital elevation model of the whole area, a shapefile which contained an estimated catchment outlet point, a value for the maximum distance that the outlet could be moved to a higher area of flow accumulation, a rainfall intensity raster for a particular storm event, and finally an estimated value for the kinematic roughness and an estimated value for the runoff coefficient. The model starts with the digital elevation model, from which a flow accumulation raster is obtained. A catchment is then generated from this flow accumulation raster, using a pour point that has been snapped to an area of higher flow accumulation. Moving the outlet removes the errors that can occur if the outlet is not exactly in the right place. Next, the maximum flow length is calculated. The maximum flow length is the distance between the outlet and the most remote point in the catchment. The mean slope within the catchment was also calculated, and these two values were needed to calculate the time of concentration later on in the model. Zonal geometry was then used to calculate the area of the catchment in square metres and in hectares, ready for the rational method equations later. Finally, two raster calculators use the previously calculated values to calculate the overland time of concentration and the peak flow at the outlet.
The limitations of the rational method. An assumption that's made by the rational method is that storm duration is the same as time of concentration. This is doable for smaller catchments, smaller than 15 square kilometers. But for larger catchments that can have time of concentrations that do for weeks, it's unrealistic. So it's not doable to say that the storm will take weeks. The illustration is showing that in case B, that is a larger catchment, the storm event is shorter than the time of concentration, and the estimated flow from the rational method is far higher than the maximum flow of the actual event. In case 1, that is a smaller catchment, smaller than 300 hectares, the storm duration is the same as the time of concentration, and the estimation is more correct. The method also assumes constant rainfall intensity throughout the storm duration. And this is a simplification of the real event where the intensity varies over time and the rain is distributed over the duration time. This can have an impact of the behavior of the flow. For example, if a low intensity period is followed by a high intensity period, the first period has already saturated the soil, and the rain under the high intensity period will all contribute to the outflow. Another simplification that the method does is assuming uniform rain distribution over the catchment area. This is unrealistic and would affect the outflow due to different properties in different areas of the catchment and the amount of rain in smaller parts of the catchment. Limitation of the input data. The accuracy of the data of a rainfall is dependent of the amount of weather stations in the area. Areas closer to the weather station are better represented for the measured precipitation than further away. This means with several weather stations, the area is better represented. Also, the instrument itself can be inaccurate, dependent on how advanced the instrument is. The representation from the measured precipitation to the interpolated precipitation value for each raster is also an uncertainty in the creating of the rainfall intensity raster. Data used in this model, the rainfall intensity raster, have a large cell size, and the catchment is only represented by 2 cells, with 1 value each for the precipitation. Because this value is the mean value for the whole cell, smaller cells gives more accurate and detailed data. The future potential of the model. Steps that could be added to the model is if we know the data for the soil type and land use for the catchment area. Then we could calculate the runoff coefficient instead of just using a value. With the soil type and land use, the runoff coefficient can be estimated from empirical data. Then the average coefficient could be calculated knowing the percentage of each runoff coefficient value for the different land use types in the catchment area. Another future potential that can be added is that the time of concentration can be divided for overland time of concentration and channel time of concentration. In this model, we only use the overland time of concentration, and it's because we don't know where the stream starts and ends. So that needs more experience and a good satellite image to get this usable values that we need. Then the flow accumulation can be reclassified to match where the stream starts. Then the 2 time of concentrations can be calculated separately and then summed together. This would make a more accurate value.